All right. In the next talk, we're going to learn how production of state-of-the-art computer chips is currently done. From ultra-pure quartz to advanced lithography techniques with emphasis on them, from silicon to sovereignty, how advanced chips are redefining global dominance. We'll also investigate geopolitical strategies in this script. So our speaker, Thorsten Hellert, is a physicist at the Lawrence Berkeley National Laboratory and there works for the Advanced Light Source Accelerator. Thorsten?
Thank you very much. It's a huge honor to be on this stage, and a big shout out to the organizing team and the people working here. I'm always very impressed in the level of professionalism this Congress is executed. Yeah. So I thought I want to start my talk by that's funny. Anyway, so I wanted to remind everyone about the scale we are talking about when it comes to modern-day semiconductors. So this is a human hair. It's about 100 micrometer in diameter. This small section of about 10 micrometer is a SSD chip. It's not even the newest one. It's from 2015. And what the people from SAIS did was they took electron microscopy pictures and then they etched away layers of atoms, and then they did another electron microscopy picture, and that's how they did a 3D reconstruction of this memory chip. And you can see all these wires here. These are the bit lines for those of you who know how these things works. And these circular structures here, this is a transistor-based memory cell that is able to store 1 bit of information. And if I did the counting correctly, this whole block holds about 500 bytes, so about a millisecond of modern video, and the smartphone that I have here has 500 million times this. So I hope by the end of this talk you get some idea of how we can build these kind of structures. But first, I want to start by briefly explaining a transistor. I don't want to go into the details too much because it gets quite technical for anyone who doesn't hold a degree in material science, but in short, it's a silicon-based electronic switch where you can apply a small voltage at the gate and then you can close this electric circuit. And as an engineer, these kind of switches are really nice because you can build more complex structures, like, for example, this AND gate by just combining 2 transistors here. And this AND gate gives the true output if both inputs are true, right? I guess most of you have heard about this. And with these kind of gates, they are the building blocks of pretty much every electronic device you can think of. For example, this very simple logic switch, logic chip, which does nothing else but adding 2 4-bit numbers. Over the decades, the design of transistors has advanced quite a lot. It's got more and more complexity, and I don't want to talk about any of these details. Again, something very complicated if you go into it. Instead, I want to simplify everything and use the size of the transistors as a proxy for technological advancement in this talk, knowing that in the recent years, the marketing teams of chip manufacturers took over, and these process nodes, as they are called now, are not directly related to the physical size of a transistor, but more to the equivalent size. But that's another detail I don't want to mention in this talk. So let's just use transistor size and process nodes as synonyms. Okay, so with the decreasing size of transistors, we have been able to increase the amount of chips, the amount of transistors we can put on a chip by many, many orders of magnitudes in the last decades. And this has led to a dramatic reduction in cost and computing power consumption for the compute. And these scaling laws, they are the reason why we can build all this modern consumer electronics that we are now used to. And just to give you an idea of how steep these scaling laws are, if you look at the cost and apply this to cars, fully knowing that you cannot directly apply this to a macroscopic object like a car, but if you could, it would mean you buy a 15-year-old Golf for $20,000, and today it would be cheaper to buy a new car than to refill it at the gas station. Right, so that's pretty significant, I would say. And another angle that I find fascinating to look at this topic is the amount of transistors we have built over the last decade. So these are the numbers of transistors that have been shipped or that are in the world, if you will. Very large numbers. To give you some idea, in the 70s we have built more transistors than there are stars in the Milky Way. And then in the 90s we have been able to build more than the age of the universe in seconds. And in 2010, roughly, we had more transistors than rice corns on that famous Chinese chessboard, which is often used as a figure for an absurdly large number, right? And in 2024, it was estimated that we have built more transistors than there are stars in the entire observable universe. And this, if you look at this machine from the 1950s, back then it was a high-tech transistor manufacturing machines at Bell Labs. If you were to run this machine for the entire age of the universe, it would produce as many transistors as we have built in the last 4 hours. It's very impressive, right? Or differently, you could say that every second we build 400 billion transistors since 1950. But this is only possible because we have been able to build ever-advancing manufacturing tools for these semiconductors, most importantly, the lithography tools with different light sources, immersion technology, and the latest advancement in extreme ultraviolet lithography. And I want to talk about these kind of advancements to some extent in this talk. Also, this doesn't only apply to consumer electronics, but since the very beginning of modern semiconductors or transistor in general, there was a very strong connection between national security and the advancements of these chips, right? From early guidance computers of ICBMs to modern fighting jets and drone swarms. And it comes as no surprise that because of this ever-increasing complexity in lithography tools, or in general the amount of money you need to build these new technologies, there has been a significant consolidation in the number of manufacturers that can keep up with this ever-increasing demands. And from a national security point, this is of course a huge problem. If you want to build an F-35, for example, there are chips in it that can only be produced in Taiwan. And of course, the US doesn't really like that. And keep in mind, this is a logarithmic plot. So this means 99% of all chips have been built in this little, in the last couple of years, right? And if you can extrapolate this now, you see the big geopolitical problems that comes with that. And in this talk, I also want to point out some of these bottlenecks and tensions that arise from that. But let's go to the chip production. One thing that I want to mention is how we, or like a comparison to lithography, it was the manufacturing of letters, basically. The invention of the printing press, probably all of you know this, has dramatically reduced the number of costs it takes to create a book, or basically to print letters, right? And with that, we had an explosion in books. And what we do with semiconductors is comparable to this technique. It's called lithography or photolithography because we use light for that. We have a light source and we shine light on a mask where we have the feature that we want to print on our chip, and then we have a projection optic which projects it down to the wafer. In the following slides, I want to go through these steps, or at least some of the details of these steps, starting with the wafer. And it all starts with quartz, or ultra-pure quartz, because we want to be cost-effective. And it's basically sand, but the purest form of sand. The 90% of this sand gets mined in one mine in Spruce Pine in North Carolina. Some of you might have heard about this last month when Hurricane Helene devastated North Carolina, and the whole industry was in big uproar. They were nervous because no one really knew the implications of this global supply chain. In the end, it turned out to be not that dramatic, but that's, speaking of bottlenecks, there's one right away at the very beginning. Then you purify the quartz and make it really very pure. And you melt it down to about 2,000 degrees, and it takes about 2 days to grow this single crystal. So you control the temperature, the humidity, everything very tightly, and you get a single crystal, like a microscopic object. It's about like half a meter, like this big, 2 meters long. And then you polish this, slice it into pieces that you can handle a bit easier. And if you have the slices, you do chemical and mechanical processing to get an extremely flat surface. So this is I want to emphasize, this is a single crystal of silicon that is then used as the ground foundation of these chips. And for the smaller process nodes or smaller transistor sizes, if you will, the demands on this surface here, on the quality, the purity has increased, which you can see here in the cost for one of those wafers. Then when we have the wafer, finally in this animation, I want to show you how we print a structure on it. So first we apply the photoresist, which is a photoactive chemical, very thin layer, and then we can print the mask, the feature here on the photo mask, on it. And the area that is hit by the light reacts chemically. In this case, it is possible then to solve it away by some solvent. So now you have this structure on the photoresist, and in the second step, in this example, you apply some plasma edging, then you have the 3D structure. In this case, then you apply a thin layer of gold as a gate, and then you can apply a copper layer. This is all, of course, atom by atom, basically, and then you polish it to exactly the right size, and you have one layer of your chip, in this case, a couple of wires. And you repeat this process up to 100 times over and over with a perfect overlay to finally have that chip. And I could talk 30 minutes easily about any of these steps. Very interesting. If you want to look into that, do it. It's fascinating, but I don't have the time, and I want to focus on the exposing step and the photolithography. One of the things that I found very fascinating is the photomask itself. So it started in the 70s here by manually cutting the shape in ruby-lith film that gets then down projected. So hand-drawn transistors, hand-drawn wires, but of course in the modern day this is not possible, so you use electron beam printing, and in this whole photomask there are literally zero defects. If there's one error, you either repair it or you throw it away. And the amount of resolution here is very impressive. So the final picture, once you project this down on the chip, is 30 millimeter and 26 millimeter. That gives 5 terapixel. And 5 terapixel is like really big camera. If you would blow up this Intel Core i7 screen to where the pixel has the size of a regular pixel of an HD TV, the screen would be about 800 meters high. And you can imagine the quality demands on your projection optics if you want to, right? It's really impressive. And you can imagine probably if you want to design a photo mask like this, you cannot do anything by hand anymore. Like an example from NVIDIA, the Hopper chip has 80 billion transistors, and every 2 years they build a new chip. That's very hand-waving, but that's about 100 million transistors per day. Of course, no one can. Right? That's like you need a very sophisticated software tool in order to design and optimize all of this. And just one layer of this photomask file finally has about 150 gigabyte in size, and you need 100 of these layers. And it's not just the photomask design itself, but once you have your design, you have to prototype it before you print it in the silicon. So you have rooms full of FPGA racks where you implement your design to test it in reality. And you also have to do high-fidelity simulations like thermal simulations on your chip, because you have different parts of the chip that heat up differently. And if you are at 3 nanometer process nodes, just the differential heat expansion or thermal expansion already can cause a problem in your overlay, right? All of these things. It's crazy what you have to think about. And this led to an absolute explosion of the design costs of these modern chips. Like the newest Apple one is a 3 nanometer process node. It's expected to have cost 1 billion, just the design. Like not the fabrication, nothing else, just the design. And there are only 2 companies in the world, Synopsys and Cadence, that you have to use when you want to design any of those chips. 2 US-based companies, so another bottleneck in this supply chain, if you will. Before we go further into the details of these photomarks, we have to talk about diffraction. just a little bit. I don't want to go too deep into optics, but when you want to project something, like let's assume this is a photo mask, and you use a wavelength that is comparable to the feature size of your mask, then you have to keep diffraction in mind. Right, and there's a Rayleigh formula giving you the smallest possible feature size, which is related to the wavelength, the numerical aperture, which is roughly the aperture of your device, and the K factor. It's literally called K1 factor. And basically it tells you that you have some physics and geometry here and illumination tricks. That means if you now decrease the feature size by not changing anything here, then you get a blurry image eventually on your focal plane, which is not what you want. Right, on this plot here, you can see how the wavelength that was used in these lithography processes has decreased. So over the years, people have, from mercury lamps, eventually came up with XML lasers, cryptofluoride or argon fluoride down to 200 nanometer, which is already pretty small wavelength, if you will. Finally, then a plasma-driven EUV. We'll come to that later. But you can see here that in red dots, the process nodes have eventually become smaller than the used wavelength. And this is primarily because people came up with these kinds of illumination tricks. And one very basic one is you can just tilt your illumination optics, and now you have the first order diffraction passing through the numerical aperture. If you want to want to learn more about this, there's a nice YouTube video here that is linked. But most importantly, the system or the process has moved from this classic photolithography to what they call computational lithography. So you start with a feature that you want to print on your wafer, and then you throw a bunch of computation on it, mostly Fourier transformation and convolutions, to figure out what kind of mask shape and what kind of light source do I need to get the feature that I want. I want to show you a couple of examples. So you start with the design here, 250 nanometer, let's say. This is what you have in your software, this is what you put on your mask, and this is the feature that you get on your wafer. Okay? And now you decrease the feature size, you don't change anything else, and if you wouldn't change much and just decrease the feature size, you get a blurry image. So instead, you can design your mask to account for this kind of diffraction that is going to happen, to again end up at this pattern. And if you go further, you can play with more tricks, like you can add a phase shift mask that actually really changes the phase of the light that shines through it. Very fancy thing. And you can combine that with optical proximity correction to get even smaller sizes. But it doesn't stop there. People got more and more advanced. As I told you before, you can also optimize the source. So instead of using a homogeneous circular light source, right, this red means full intensity, so this is basically a circle, you can optimize the light source to get a multipolar field and end up with this kind of mask to add end up with smaller and smaller features. Now, this is very fancy technique, in my opinion. This is an example here from ASML, where you can see they have all these adaptive mirrors, and they can really on demand change the light source to whatever they want, basically, to increase the resolution of the printed machine. But as you can imagine, this means you need to have a lot of computation in order to get all these shapes in the right form. One example here, that's from a talk from NVIDIA, they have now, we're well in the trillions of polygons that are included in each of their chips. And just at TSMC, we have like 10,000, or way above 10,000 chips that are produced every year. And the computational demands just for this optical proximity corrections are now in the billions or hundreds of billions CPU hours, or if you want to count that in 15 megawatts data centers, we are now at like 10 to 100. Right? And I found it very interesting that NVIDIA actually throws a bunch of money in developing Litho, which is a hardware-accelerated software tool capable of doing these kind of calculations. So it's this flywheel where NVIDIA tries to develop the most advanced chips, but in order to do that, they need to develop the software that allows them to, and so on. I found that really fascinating. Okay, sorry. But eventually, there's no room for just throwing more computation on it. The physics just strikes back, and you need to get a better light source. So now let's look at the extreme ultraviolet light source. This is actually the easiest way they found to generate this kind of light. It sounds kind of crazy, but it's actually really the easiest way. So we shoot a bunch of tin droplets, molten tin droplets, a couple of micrometer in size, with a velocity of 280 kilometers per hour into a vacuum, and then you hit it with a pre-pulse of CO2 laser, which makes the tin droplet to expand. And then you hit it with a 13 kilowatt main pulse, also a CO2 laser. That's like steel cutting power. It's really a lot, which instantly creates a plasma which is much, much higher than the surface temperature of the sun. And this then emits the EUV light, which you then capture with a giant mirror here in the back and project it into the projection optics. So there's only one company that was able to build this kind of laser. It took 10 years and a couple of $1 billion in R&D. It's TRUMPF. And there's only one company that was able to build these mirrors, which I would like to talk a bit more. So everything has to be in vacuum here because EUV light gets absorbed by pretty much every matter. So you cannot build any lenses in order to steer that light. You need to have Bragg mirrors, which act with these, like, have this constructive, reflective processes here. You have layers of silicon and molybdenum. You can see here a real picture of those. It's a 10 nanometer, so you have a few layers of atoms. And the stability of these mirrors is absolutely crazy, I think. So they are actively controlled to be more precise here. This is an actual measurement that's 0.2 nanometer. 1 nanometer, by the way, is the distance your fingernails grow in 1 second. So they control these mirrors to a fifth of that, or even lower, while in operation. And the angular stability, 0.6 nanoradian, what that means is you could shoot a laser and hit a golf ball on the moon. Right? It's really remarkable technology. And the surface deviation, the acceptable surface deviation here is 100 picometer. The mirror is 45 centimeters in diameter. If you would blow this up to the size of Germany, it would mean the highest mountain is the human hair. So these are the flattest objects humans have ever built. And I want to show you this video from ASML. It's their newest machine that just came out. It's the high numerical aperture EUV lithography machine. It costs $350 million. It's the most complex and most expensive machine humans have ever built more than once. And this is right? I mean, we built the LHC, but not in mass production. So here you have the same kind of light generation. These are the tin droplets that you hit with a pre-pulse, and then with the main pulse, you have this plasma, the UV light. These mirrors here are now almost 1 meter in size, and this is the mask, the optic mask. It's a 30G generation, back and forth scanning. That means like you get to 100 kilometers per hour in like 9 milliseconds. And then you hit the wafer stages. You have a metrology stage first, so now a new wafer gets inserted and gets measured with this laser, and they claim they can align everything to 4 silicon atoms. Right? While this thing is accelerating at 32G. No idea how they can build it, but apparently it works. It's very expensive, but it works. And yeah, throughput of 185 wafers per second. So of course, all of this is in pure ultra-high vacuum while you make these tin droplets explode and so on. So really crazy, and there's just one company that can build this. It's ASML. It was founded in 1984 in the Netherlands. Today it's worth $400 billion, and it's the 4th biggest company of Europe. And they make their revenue mostly by EUV lithography tools and argon fluoride immersion tools, as you can see here. It's pretty high revenue, and they spend a significant amount of their money in R&D here. Just as an example, this is the comparison, this is the CERN budget. right? And with this, they have been able to capture pretty much the entire lithography market share in the last decade. So right now they are at 90%. There are two competitors from Japan. They are basically now at 5% roughly, and ASML is the only source or the only company that can build this EUV lithography. There's not even a single other company that is even trying at this point. Everyone else gave up because they thought it's too expensive, it would never work. So right here on this picture, you see, I don't know, $1 to $2 billion in high tech, and in one of those factories where the chips are produced, there's not one of those machines, but hundreds of them. As you can see here, and this brings us to TSMC, Taiwan Semiconductor Manufacturing Company. It's pretty much the main player who builds these chips, who buys the products from ASML. This is a factory they just started building in Arizona. It had a lot of fuss in the US. I don't know if you know about it, but it's actually, you can see it's a pretty big facility, right? But in TSMC terms, this is called a mini fab. They also have mega fabs and giga fabs. They really have a trademark on this. They are all located in Taiwan. They cost $20 billion. They use a gigawatt in power, 8 million liters of water per day, and they have a throughput of 100,000 wafers per month. So you can see that's an economy of scale here. And with this huge factories, TSMC was able to capture a big market share. Here, these are old numbers from 2020. Right now, it's even more concentrated towards TSMC and Taiwan. But even then, you had like 60% of all chips that were made by TSMC, and most importantly, 92% of the most advanced chips that were built by TSMC. And there's only one other company, Samsung in South Korea, that can build those. And in order to do this, they need to spend $30 billion per year just to keep their factories on the most modern state. And they can do this because they have, it's again this flywheel of economy at scale, because they have so much market share, they can ask for gross margins of 60%, which is even higher than Apple or Nvidia, right? And that's how they can generate all that revenue and earnings to put $6 billion a year in R&D. And they need this because here this is a plot of the fractional revenue of TSMC by different process nodes, and you see every couple of years there's a new node coming up, which means basically a new factory that you have to build with new R&D. Like this is like a really, it's not just a factory, it's basically a research project that you have to build. And as I said before, because of this very fast pace and these huge capital investments, more and more companies gave up, and right now there are only Samsung and TSMC left with the newest nodes. And all, or pretty much all, they have a factory in China and one in Arizona and also one in Japan, but most of their production is in Taiwan, all located on the West Coast. Now you could ask, what could possibly go wrong? And I want to mention two things that come to mind. One of them, you've probably heard of the Pacific Ring of Fire, right? It's a region with a lot of earthquakes and volcanic activity. And when I did the research for this talk, it was December 15, I Googled on my phone Taiwan earthquake, and this was the Google landing page. So just a few days before, there was a 4.1 earthquake just across the coast. But actually in April, there has been one with a 7.2 magnitude, and you can see this was quite a shakeup. Right, and remember all the nanometers that I was talking about? So this one was far away, the epicenter was far away from the production sites. TSMC had to shut down for 1 week and lost a couple of $1 billion, but they had been able to ramp up the production in 1 week. But no one really knows what happens if a major earthquake hits the production centers. Another thing that is maybe even more dangerous, or I don't know if you want to say that, but at least also very dangerous, is the geopolitical tension that comes with that. You probably know that Taiwan has a pretty strong democracy, and they recently had an election where a China skeptic won it and is now the president. China didn't like that. In their eyes, Taiwan is part of the People's Republic of China, and Xi regularly says that the reunification with Taiwan is inevitable, to which Taipei says nope. And the US, its biggest security partner, recently said that we would intervene militarily if Taiwan gets attacked. The Chinese Ministry of Foreign Affairs just 2 months ago said that Taiwan independence is incompatible with peace in the Taiwan Strait, which is pretty strong words, right? And it's not just words, but it's backed up by significant military power. So the PLA Navy has way surpassed the US Navy, and they have spent a significant amount in their development of ballistic missiles. Especially anti-ship missiles, which are called aircraft carrier killers, with a range of a few thousand kilometers to keep the US Navy out of the Taiwan waters. And not only these weapons development, but they also have regularly exercises, like just recently, basically the biggest military drill in modern Chinese history. And this is a video here from Chinese state TV, where they actively show their plan for an aerial bombing campaign and then an amphibious landing, including the capture of the government in Taipei. Taiwan hopes that TSMC is their silicon shield, that's what they call it, because all sides would have to lose, would have way too much to lose for this, to let this happen. For example, here you may remember the chip shortage during COVID that estimates that the car industry had cost about $200 billion, and that was a relatively localized chip shortage. There are estimates that show that the blockade of Taiwan would cost, like this is a drawdown in world GDP, is in the scale of the global financial crisis or COVID-19, and an outright war between China and Taiwan would roughly double that. And that does not even include the US response or a bigger war on a global scale, right? So this is a pretty bleak outlook, quite terrifying actually, but I don't know how this is going to end. I don't want to speculate on this, and I don't want to end the talk with this horrific picture, so let me shift your attention to this marvelous piece of technology again. Which I just have one more slide. Thank you, though. I work with particle accelerators, and I'm used to work with the cutting-edge technology, but when I did the research of this talk, I was really, really impressed by this technology, and I never thought that this famous quote from Arthur C. Clarke is more true, that any sufficiently advanced technology is indistinguishable from magic. And when I did the preparation of this talk, OpenAI Sora came up, and I used this picture and 10 minutes of prompt engineering to ask it how it looks from the inside. And I want to show you this little video, which I think is another pretty advanced technology that is unfolding right now. Right. All right. Now, thank you for your attention.
Another fascinating talk by Thorsten Hellert, after we have already seen him in Leipzig with X-ray free electron lasers a couple of years ago. So thanks again for this beautiful talk. So we have time for a couple of questions. Please line up at the microphones. In the meanwhile, we already have a question from the internet. Please.
The internet is amazed and would like to know how long did it take you to collect all this information and visuals?
2 months, pretty much full time.
And now let's start with microphone number 1.
Yeah, hi, thanks for the amazing talk. I was working in semiconductors like in the early 2000s, and back then the professor said it's going to be 10 years and then we're all going to die to power death and it's not going to work. Now we are like almost 25 years later, and we are at this scale how far does it get? I hear Moore's law is dead now for a couple of years already. So what do you see? How far does it take us?
Yeah, that's a very tricky question. I can't answer that. What I saw when I researched this talk, I saw a lot of information or people who know way more about the industry than I do, and they said something like 20 years maybe they can keep this up with the thing that they have already lined up with the physics that is known, where it's just a manufacturing issue. I mean, the main thing here is always an economy. That's the big issue. It's not what is physically possible, but what is possible to a price that we are willing to pay, right? That's the big challenge here.
Okay, next question from microphone number 3, please.
Yeah, thank you for the nice talk. I wish we, over here, I wish we had a similar amount of money at CERN and other high-energy physics facilities compared to what ASML has. My question is it known how fast China is advancing and producing machines like those from ASML? Because they could just bomb Taiwan on their own and just have a monopoly themselves if they get advanced enough in the near future.
Yeah, it's a very interesting detail that I find it fascinating. China throws, like in the last 2 years, they threw $100 billion on this, like two $50 billion subsidies, like a CHIPS Act every year, basically, and they see this as their biggest issue, right? The sovereignty from Taiwan and the US, and estimates are they are 10 to 15 years behind ASML, and also TSMC. I don't really understand why, because I would think that the Chinese also their intelligence capabilities, right, that they are able to get this kind of knowledge. But apparently TSMC and ASML, they are really good in keeping their secrets.
I mean, you outlined it's not just TSMC and ASML, but also Zeiss, Trumpf, and
Exactly.
the manufacturers
Yes,
that also
yes.
ASML relies on.
And like decades of,
Yeah.
right?
Thanks.
Okay, next question from number 2, microphone, please.
Yes, you mentioned Cadence and Synopsys as main design software, but there's also a German company, I think Siemens, the mentor. They also do a little bit in that business.
Yes, sorry.
And are there also open source alternatives for those kind of tools? Because there are several talks about FPGA and logic synthesis, but never something about high-level synthesis that probably NVIDIA has to use to make all those transistors.
Yeah, I don't know, I'm sorry. But I just saw this information in a few sources that if you want to build these cutting-edge chips, there's no way around these two companies. But I know that Siemens is there with a small niche, but sorry, I cannot answer the open source question.
All right, microphone number 4, please.
Yeah, I was just wondering, these final structure sizes, do they affect the lifetime of the transistors significantly?
Not that I know of, but I don't know if that's... Actually, I don't know, but I didn't find that, I didn't see that information in either direction when I did the research, but I don't know. I would think that there should be an effect, but maybe the quality of the the materials that you use have a bigger impact. Right, because of course, if you have only one atom and then you have a gamma ray, then if it hits that atom, then the transistor is gone. But there are probably other effects that are more important than this one. I don't know.
Okay, do we have any questions from outside internet? No? Okay, so then let's go back to microphone number 1, please.
Yeah, thanks. What do you think are going to be the next technological steps, and what kind of physical limits are we going to hit finally?
So I think the next steps here are these nanosheets that I showed at the beginning, but it's something that I didn't talk here because it gets really complicated and it would be very far from the topics that I wanted to talk about, but it's like the way. Like if you remember the video that I shot at the very beginning of these layers that you build on top, like basically if you add more and more layers, you can build more and more complex 3D structures, right? It's like you print 3D by adding different layers, and I think this gets more complicated in the future.
Thanks.
Again, thank you very much, Thorsten, for this really nice talk. Again, an applause from the audience, please.